Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to start with the lecture number 21, and in this lecture we will do assembly programs whatsoever we learned in lecture number 20. In lecture number 20 we learned about conditional and block structures. So in this lecture we will do all the assembly language programs and implementations. So this is review for lecture number 20. In lecture number 20, the first statement or first instruction that we studied, it was the bit test instruction, and in this bit test instruction there was a BT keyword and then bit base. So the base can be a register or memory location, 16 or 32 bit register or memory location, and then we have the bit number. So we want to test this bit number, either this bit is 0 or 1. So this bit will be transferred to the carry flag, and then we can check either the carry flag is set or reset based on the value of this bit. Then we will quickly look over all the other instructions such as loop E or loop Z. So these are the conditional loop instructions based on the equality and zero flag. So the syntax of these two instructions is like the loop E or loop Z keyword, and then the destination label where we want to transfer control to the label. And the logic behind these two is that we know that in loop ECX is used as a counter, and in every iteration when we call this loop E or loop Z or even the loop instruction, then ECX is been decremented, and then in this loop E and loop Z what will happen? So first, this is the condition that is being checked, that either ECX is greater than 0 or not. If ECX is greater than 0 in loop statement or loop instruction, then flow will transfer to the jump will happen to the destination. However, in loop E and loop Z, this condition is also being checked, either the 0 flag is equal to 1 or not. So there are two conditions that must meet to check to jump to the destination or jump to the label. First condition is if ECX is greater than 0 and 0 flag is equal to 1. These type of instructions are useful when we are scanning an array for the first element that does not match a given value. So if it doesn't match, so we can continue this loop. Similarly, there are other instructions like loop NZ and loop NE. So loop NZ is not 0 flag and not equal. So the syntax is almost similar, and this one has only one condition which is different from the loop Z and loop E, that is that if ECX is greater than 0 and 0 flag is not set or 0 flag is equal to 0. So these two pair of instructions are the conditional loop instructions. Then we discussed about the conditional structures like block if structure, how we can use this block if structure, then how we can evaluate expressions inside assembly language, and also compound expressions with and or logical operators. Then we implemented them in while loops, the while loop condition and repeat loops in assembly language without using the while directive and repeat directive and so on. Here we will go through all this one. So this is the if structure or the block structured if statement. Here we write in high-level languages, for example, as we discussed in previous class. So the same instruction or same block structure if structure can be converted into the assembly. So here the logic is if operand 1 is equal to operand 2, or here can be any relational operator less than, greater than, and whatsoever. So the logic is here that we compare these two, operand 1 and operand 2, and then jump not equal whatsoever the condition we use here. So here, for example, it is equal, here we are using not equal, then we can directly jump to L1, and then in case if this condition is, for example, true, if we compare both of them, if they are not equal, we will go to L1. Otherwise, what will happen, x will be added with the or x will be assigned a value 1 if they are equal. So the same condition is, if they are equal, x will be added with 1, otherwise x will be assigned a value, x will be assigned value 1, otherwise x will be assigned value 2. So this was about the block structured if statement. Similarly, there are other ways. For example, if we use compound expressions, here you can see the expression is, there are two expressions, and we are using different two expressions, and they are combined with the AND logical operator. So here, in case of AND, for example, this should be true and this, both of these should be true. When they both will be true, then definitely whole condition or whole expression will return value true. And if whole expression is true, then this x will be assigned value 1, for example. So here you can see this is the logic that we have implemented, or that we will implement today in the assembly language. So what we do, we compare first AL and BL, and then we will check either this condition is true or not. Now one thing, if this condition fails, it means there is no need to check for the next condition, because if this is 0, this fails, then definitely we don't need to check second condition, because it will automatically be false, and so on. The whole expression will be false. Now here, what we are going to do, first we check either AL, compare AL and BL. So if we will jump above, if AL is above BL, then we will jump to L1, means we will compare to the next expression. Otherwise, if this condition is false, or AL is not above or greater, larger than the BL, then we will jump to the next. So next is the exit from this condition. If this condition is true, definitely we will jump to L1, and then we will try to compare the next condition or next expression. Similarly, if next expression is, for example, true, then we will jump to L2, so we will assign value 1 or move value 1 to x, and so on. Similarly, if there is OR, if we use logical OR operator between two expressions, and this whole expression will be true if any of or maybe or both of these expressions are true. If this one is true, whole expression will be true. If this one is true, then whole expression will be true. If both are true, then definitely whole expression will be true. So similarly, there is one logic we have implemented here, and we will test it in today's lesson. Now there are while loops. We know that while loops are repeated until this condition is true, and the same condition we can use, for example, EAX is less than EBX. So this loop will continue until EAX is less than EBX, and so on. So the same way we can implement, like in the previous example we saw the conditions. Here you can see the implementation. So this is the loop condition. Here is the this is compare EAX and EBX. This is the loop condition. So check the loop condition, either EAX is greater than or less than EBX, and so on. So first we compare, then we will assign the condition for the jump. So if jump above or equal, so if condition is false, then exit from the loop. So next is the exit from the loop. So our loop is from here to here. So what we are going to do, we are incrementing EAX and jump to top. This is unconditional jumps. So we just define the condition to exit from the loop. Otherwise, there is unconditional jump to the top. So it will again and again jump towards the top of the loop, and so on. Similarly, we have the if directive. So in this if directive, this is the if, dot else, dot end if, or dot else if. All these are directives. And there are two other directives, like this one is the repeat directive and the while directive. So repeat directive is used with the until directive, and while directive is used with the NW or end while directive, and so on. You will see examples here. So these are used to check the expressions at the runtime. Here is one example. For example, if EAX is greater than EBX, this is directly you can use inside the assembly language. There is no need to use the logic. If you want to use the pure assembly logic, then you can use. Otherwise, there are some directives you can directly use them. So .if directive will check this condition, .eax is greater than ebx, then it will assign 1 to edx, else edx will be assigned 2. Now we are writing this one, then definitely these are the directives for the assemblers, and assembler will generate assembly code or the machine code accordingly. Accordingly means the previous code that we discussed, the same code will be generated based on the values of these, based on the logic that we are using. For example, if we use ex is equal to ebx, ex is less than ebx, and so on. So, and either we are using signed or either we are using unsigned values inside the ex and ebx and so on. So it depends on these values or depends on these logic. The assembly code will be created by the assembler and so on. Here you can see we can use compound expressions. So if ex is greater than ebx, or ex this one is AND. So if ex is greater than ebx and ex is greater than ecx. So this is a logic compound expression that is being used here, and we have, if this whole condition is true or whole expression returns value true, then edx will be assigned value 1, otherwise edx will be assigned value 2. So you have to keep in your mind that we have .if directive, then .else directive, and .andif directive, and we have also another directive is called the .elsif directive. You can use also this one if you have repetitive if statement, if inside the if directive inside the if statement, or if directive and so on. So this is the same logic which we use in high level languages, like when we use if, else, else if, and so on. So the code will be generated accordingly by the assembler. And here is the repeat directive. So for example, we saw that in repeat directive we have the keyword .repeat, and the condition is being checked in until directive. Now in this repeat directive we already discussed that this whole loop will be executed once, even though this condition is true or false. Whatsoever the condition is, this loop will be executed once. So for example, we are starting with the repeat directive, and repeat directive will continue from here up to here. So this loop will execute once. Now it depends. If this condition is true, then it will repeat again, otherwise it will not repeat again, and so on. So it executes the loop body before testing the loop condition associated with the until directive. On the other hand, we have the while directive and end while or NW directive. So this is almost similar, but the condition is being checked before the loop starts. For example, in the starting of the loop, first we check the condition. While eax is less than 10, so we start this loop. If eax is less than 10, if condition is true, this loop will execute, or body of the loop will execute. Otherwise it will exit from here to the next statement after NW. And in the NW, when it will reach to the NW, what it will do, it will again forward control or transfer program control back to the while statement. Now these were all the instructions, simple, very brief review what we did in our previous lecture. Now today we will do all these instructions and directives that we discussed in our previous lecture in assembly language. Okay, so now we have started the new project, and the name of this new project is lecture 21 example 1, and we have one file, assembly file. Inside this lecture 21 example 001 is called the lecture 21 example 001.asm, and now we have included, this is the skeleton program you can see here. So we have .386 directive, and we have model and option cast map, and we have included the Windows kernel 32 include and library files, MASM 32 include and library files, and so on. Now we are going to start with the first one, like the bit test. So there is nothing inside the data directive and between the data and code directive. For example, if we want to test the bit test, how we can test? For example, if we say move EAX comma 37, for example, and we say BT EAX comma 2. Okay, this is simple one. This is very simple program. What we do, we will just build. So this build is successful. We just run this program, and we will try to see all the registers. Okay, I think now it's okay because it was a bit slow. So here we will try to see the flag registers. So the carry flag will be set or reset based on the value of the this bit. Now if we continue, now this is 25 in hexadecimal is 37. So 25 in hexadecimal has been assigned. If I say what is the status of bit number 2, so you can see carry flag is set, is transferred with 1. How it is being transferred? Because this 37, or you can call it like 25, for example 25. If we say 25 in hexadecimal, then 5 is like 4 and 1. And if we see the bit number 2, so bit number 2 has the value 1. I can write in hexadecimal, for example 77 in hex, for example, and I just write 0000, so 246. Okay, just save this one and build this one. I just build this one. So 1 is updated. Now I just run. Okay, now here you can see first one is the 77. So for this 7, definitely all the bits in this 4 bit, all these least significant 4 bits, out of them 3 will be set to 1. I want to see the bit number 2 either set or not. So if it is set, it will be 1. If I write here, for example, bit number 1, bit number 1, bit number EAX comma 2, bit test EAX comma 3, and so on. So here you can see what will happen if we run this program. So 7 in hexadecimal definitely is 0 in 4 bit. If we convert in 4 bit, it will be 0, 1, 1, and 1. Okay. Now this is the value that is being assigned. Bit number 1 and bit number 2 is same because there is no changing, and bit number 3 is 0. If I write, okay, so if I write bit number 0, for example, here BT EAX comma 0, what will happen here? You will see I just build this one again, run this one. So bit number so this is B77 has been assigned. Bit number 0 is equal 1, bit number 1 is equal 1, bit number 3 is equal 1, 2 is equal 1, and 3 is equal 0. if I want to test the whole EAX or AX or AL whatsoever, I can test their bits. So bit number is starting from, as we know that bits are, bit counting starts from 0 and so on. So we can continue up to bit number 31 for the EAX and so on. So this was all about the bit test. I will just comment this one so that it must be available maybe in future if you need these programs. So this is for the bit test. And I will also comment this one. Okay. Now next one is the loop Z and loop NZ, for example. For example, I will start with the inside the data. I will say array 1, and this one is the, for example, signed word, and the data is like -3, -4, -5 and 0. Sorry, I don't want to put more values here, and if I say 10, 11 and 12 and so on. Now before this one, I just want to write the logic. For example, if I want to say move ESI with the offset of array 1, so ESI contains the offset of array 1, then move ECX. ECX will be used to check the logic, check the as a counter. So ECX is equal to, for example, if I say the length of array 1, and here we are starting with the loop. So here is the L1, for example. This is the label which we are using here, and now we will test. So test will perform AND operation. When we perform AND operation, definitely it is the non-destructive AND, if you recall. So if we say test word pointer to the ESI, comma, we are using 8000, okay, in hexadecimal. So this is the test for the sign bit. We want to see the first positive value, for example. So definitely what will happen, if there is a negative number, its sign bit will be 1. So if we test them, then definitely the whole output will be 0. Whatsoever the value is there, definitely sign bit will be 1 for the negative, and rest we are going to perform AND with 0 0, so it will be 0 if it is negative. And now the next one is we are going to push FD, and push FD will perform the our flag register will be pushed. So after test we are trying to save the flag register. Next one is the pop. Before pop FD we add ESI with the type of array 1, and then pop FD, because when we perform add operation, then definitely something or the it will perform it will change the flags. So we don't want to lose our flags or status of the flag. So loop NZ, loop not equal 0 means the 0 flag is not is not set or equal to 0. So there are two conditions that will be checked with the loop NZ. So for example, if we say loop NZ L1, there are two conditions. First condition is ECX must be greater than 0 and NZ must be equal to 0, and these two conditions this loop will continue. So for example, if I want to just save this one and I just build the project, so this is successful. Run this project, and here you can see first ESI ESI is equal to 20400. This is the starting address where our array starts. Our array is stored in the memory. Then length of array, definitely it is ESI. So ESI has the value. So ESI has the offset of the array, and ECX has the value, the length of the array. So length of array you can see here 1, 2, 3, 4 and 5. So ESI has the starting address and ECX has the length of the array. And now we are going to start with the testing the condition. So test word pointer ESI, whatsoever the value here in the ESI, we are using it as a word, and pointer will give us the liberty to access that value. So 800, here you can see when we perform 800 test condition, so our 0 flag is equal 0. 0 flag is equal 0 means definitely the value is 0 because negative value or the negative value in this element is sign flag, sign bit should be 1. So if we perform AND, then definitely it will become 0. Now this is the status flag register, the flag register. So we want to push it inside the stack. Why we want to push? Because we are performing AND operation here. So here we push to save this one. So we pushed here and then we perform AND operation. So AND operation performs some, you can see, changes here inside the flag register. Again we pop. So when we pop, then FD, so loop NG, it will perform loop to L1, or it will jump to L1 if ECX, you can see ECX is greater than 0 and 0 flag is equal to 0. So we have jumped here back. So it will continue. So it will check for the next one, and when it will come to the third one, definitely this element or the first element, second and third element, what will happen, it will check the sign bit. If sign bit is 0, then 0 and 1 we perform AND operation. So here is the program. In this program we have an array. So array is, there are 5 elements in the array, like -3, -4, -10, 11 and 12. So what we are going to do here, we want to move the ESI or assign ESI value of the offset or the starting address, and ECX is assigned the length of the array, and then we are going to test. So here when we write 8000, in case if it is negative, for example the value is negative, what will happen, negative has the initial for bit or the starting bit should be 1, whatsoever the other values are inside the this array. If this bit is 1, for example if we have 800, so 8, then 0, 0 and so on. So if this value is negative, so here it will continue. If this bit is, for example, for the negative value is 1, then definitely the AND operation will generate the value, and this value should not be equivalent to 0. So what will happen, 0 flag will be must be 0. 0 flag must be 0 because the value or the AND operation will not generate the value 1, not value 0. So here what will happen, whatsoever these bits are, they will be ANDed with this one, they will all be 0 except this bit, in case if the value is negative. However, if we have positive value, then what will happen, all these bits will be added or ANDed with this one, they will return value 0, and also this will return 0. So in case of positive value, 0 flag will be set. In case of negative value, 0 flag will be reset. So what we are going to do here, and this loop will jump to L1 if ECX is greater than 0, and also if the 0 flag is not set. 0 flag is not set. zero flag is not set when zero flag is equal to 0, or we can say that when until the value of these array members is negative. Now if I just save this one and build and run this project, you will see the results. So if I view the registers, so here inside the registers, these are the registers, and if I want to continue, so first ESI is assigned with the array offset. So ESI has the value, this is the value or the address where our array starts. Then ECX has the value 5 because we have 5 elements inside the array, and so on. And next one, what we want to do here is we want to test the condition. Definitely if it is negative, then value will not be 0 because its sign bit is equal to 1, and for this 8 hexadecimal its leftmost bit is 1, so it will not be 0, result will not be 0, and definitely it will reset the 0 flag. So currently if you check this 0 flag, it is set, but when this AND operation or undestructive or non-destructive AND operation will perform, then it will be reset. Now before going to perform addition or other operations, what we have to do, we have to push the status flag. So we have pushed status flag register and or the flag register, and then we perform other operations. So you can see here that this AND operation, or sorry, this ADD operation has modified some of the status flag or flags here. And then what we do when we want to check the conditions for this loop NZ, so we will just pop this one again. Now we have the same status flag which was in the previous before this AND operation. Now loop NZ, because it was negative, so 0 flag was reset, and even ECX is now 5, so it will perform loop. When it will perform loop here to L1, you can see here it has decremented. It has decremented in the ECX. So it will check for the second one, and definitely for the second one 0 flag is 0, and so on, because second element is also negative. So we have pushed and popped, and then we have incremented ESI, we went to the next element, and so on. Again loop will be performed. Now we are trying to access the third element, that is 10, and if it is positive value and if we perform test operation, then you can see here it will raise this 0 flag. You can see here, so 0 flag has been raised. Definitely this violates the loop NZ condition, because one of the loop NZ condition is that and 0 flag must be 0. So what will happen here, it will exit from the loop. Now when it will exit from the loop, you will see here that ECX has the value whatsoever the counter value is, and ESI points to that element. ESI points to that element which we want to have, which is the positive element or the first positive element. Now what I want to do here is that I want to print that value. So I will say display one, this is the byte 100 or 20, duplicate here. So after this loop, when this loop will exit, so here we will perform if jump not 0, jump not 0. So if the jump not 0 means if the 0 flag is not set, because when we exit from this loop we already saw that 0 flag was not set to where, to somewhere like if I want to write here the value, for example quit 1, and here is the quit 1 label. So at this quit 1 label, so here for example if I want to invoke invoke dw to a. So I will dw to a, the value of register, for example, is the here what I will do here, dw to a, and first of all I will subtract esi comma type of array1, and then move okay ex comma word pointer array dw to a, so ex comma address of display1 invoke is the stdout comma address of the display1. So first I just save this one. Yes. Okay. So we have the ESI, so it's only AX. Okay, leave this display right now. So here what we saw that we can find the first non-negative element. So here what will happen if we execute this one, as you saw here, that if we want to execute this one, then we can continue checking the condition for the first element, then for the second element, and so on, until and unless we have found the first non-negative element. So first we perform test operation with the ESI, and then ESI has the offset of this array, the address of this array, and we just take the word pointer for this and value from there and perform AND operation, non-destructive AND operation. And first we will save all these all these flag register, whole flag register, and increment the ESI or age 2 inside the ESI. Then we pop, and then this loop will be performed when ECX is greater than 0 and so on. So we just save this project, and this was about the loop NZ. Then same logic you can use with the Z0 and the equal and so on. So there are different logics you can use inside this one. I just save this one, or maybe I just remove this one. First I copy, and I just remove this file, and I just want to add a new file. This name is lecture 21.002.asm. So I want to paste the same logic, and I will remove everything from here. Sorry. And this array also. So we have the same skeleton program. Now we want to test about the if structures or block if structures. Now what will happen in this block if structure? We have the logic. For example, if I want to write the logic in comments, for this one the logic is, for example, if in C or C++ and high-level languages, when we write that in, for example, high-level language format of these instructions, the logic is if, for example, we write operand 1 is equal to operand 2, then we perform something. We say x is equal to 1, else inside this one x is equal to 2. So x is equal to 1 if the condition is true, x is equal to 2 if condition is false. So this is the high-level language operation or format of if statement. Now what we want to do, we want to write the same logic here. Before that one, I want to define the same. OP1 is, for example, double word, and this one is 21 hexadecimal. So this is double word. OP2 is double verse 22 hexadecimal. So we have defined two parameters. Operand 1, OP1 is 21 hexadecimal as a value, and OP2 is the 22 in hexadecimal. So the same logic which is here, we want to write the same logic here. So I just, for example, save this one. So here we write, we define two operands or two variables, OP1, and we assigned value 21 and hexadecimal 21, and OP2 as 22. And now the same logic we are going to implement here. For example, if we perform move EAX comma OP1, and we perform comparison CMP EAX comma OP2. Now these are the two, EX has the OP1 and we are performing comparison. So we say jump not equal, for example, to L1. So L1 should be here, L1, and we will perform if this condition not equal means if they are not equal, then we will come here to the x2. So L1 has move EX, for example, or maybe we can say that we define the output or operand 2 or X1 double word. Nothing has been mentioned here, so we can say move X1 comma 2. Otherwise here move X1 comma 1, and before that we say jump L2. So L2 should be here, for example. L2 should be the next logic or the next statement after this one. So the logic is very simple here. If you see both these logic in high-level language, move EX with operand 1, move EX, we compare operand 2 with the EX, and we are using not equal, equal, and so on, above, equal, and so on, because this one is unsigned one. And first, after comparison, we are checking, for example, if they are not equal means the value is either greater or either less whatsoever. So we jump to the L2 or L1 and we assign the 2 into X1. If I write here the same logic, X1 and so on. So I just save this one, build this one. So build is successful. And if I want to run this one, so first of all move EX. So EX is the value 21. Then we compare EX and with the operand 2. So after comparison, definitely they are not equal. If they are equal, then zero flag must have been 1. So jump not equal, so it will jump to L1, and definitely X1 will be assigned value. X1 will be assigned value 2. So after that it will exit from the program. However, on the other hand, if they are equal, if these two values are equal, means if I assign 22 to operand 1, and if I build the solution and run again, so first statement, okay, move EX. If they are equal, after comparison, if they are equal, then definitely zero flag will be 1, and then this jump will not be performed, because this jump will be performed when they are equal. For example, operand they are not equal, so operand 1 and operand 2 they are equal, so X1 will be assigned value 1, and then jump L2 or exit from this if statement. So X1 is comma 2 will not be performed. Similarly here, if they are equal, X1 will be assigned value 1, otherwise X1 will be assigned value 2. So this is the way you can implement that logic. However, try to make it more efficient as you can. On the other hand, we have, for example, the next statement that we want to use, a high-level language format that we want to use. So if operand 1 and is equal to, for example, EX is less than or equal to, I think I just I just copy this one and close this one. So this is the new file. So what I want to do here, actually I want to write them in separate files, and here I'm trying to use the registers, for example, and the logic is, for example, operand 1 is less than or equal to, for example, is less than or equal to operand 2. Okay, what will happen here, I want to use not this one, so there's compound here and here. So these two will be, for example, if I say the EAX register EAX will be equal to or assigned value 5, and EDX, for example, EDX will be assigned value 6. Okay, so this is the logic. Now what we can do here, if operand 1 is less than or equal to operand 2, so if operand 1 is less than operand 2, then what we have to do, we can perform the operation. So the same thing, for example, we can assign value move EA, if I want to write here EBX and ECX, for example, and move EBX comma 10, move, or maybe if I want to use 9 here, move ECX comma 10 here, or maybe, for example, before that one I want to check either it does work or not. So I want to check the other conditions. Move to, for example, next one, and here I defined next one label. So what we are going to do here, if we compare them, first we compare EBX comma ECX. EBX and ECX, they are being compared, and after that we say if jump above means if EBX is above then the ECX, then it will jump. However, the logic is if EBX is less than or equal to ECX, so what will happen here, we will not assign any value to EAX and EDX if EBX is above ECX. So here the logic we are implementing is really opposite, but the work will be done as we want. So here you can see move EAX comma 5, move EDX comma 6. Okay, so here is the invoke statement, or next statement is the invoke statement, and so on. So what you can see here is that we have simple program or simple logic. If EBX is less than or equal to ECX, then these two registers will be assigned value 5 and 6 respectively, and we have assigned values. Initially we initialize two variables to EBX and ECX, then we compare. If jump above, then we just jump to the next one. So I just save this one, build the solution. Okay, so solution has been built and it should be successful. Okay, now what we do, we just move EBX with 9, ECX with 8, compare both, so they are being compared, and jump above. If EBX is above than ECX, it means it is not less than or equal to ECX, so we will jump to next, or the statement which is here near the label next one. Okay, this is the logic when we have otherwise if I'd assign 10 here, then definitely 9 is less than 10, so I just build this one and I just run this one, and now in this case if this condition has been is true, then definitely EX will be assigned 5 and EDX will be assigned 6. So EBX is 9, ECX is 10, compare both, jump above. So EBX is not above ECX, then what will happen, EX will be assigned 5, EDX will be assigned 6, and so on. So in this case you can implement any of the logic. So after assigning this one, it will move to the next statement after whatsoever the statement is. Now this is when we are going to implement all these. Now if we have else, for example, here we have else statement. If we want to use else, if variable 1 or if variable 1 is less than variable 2, And if we use else statement, for example, so we say here, if I want to write variable 3 is equal to 10, else and we have here compound or the body of this else. So inside this one, what we define, we assign to, for example, if I say that variable 3 is equal to 20, or for example 2, and variable 4 is equal to 5. Okay. So what I want to do here, I want to define the, for example, variable 1 double word 4, and I want to define all the other variables. Variable 2 is equal to 5. 3 and 4, I don't want to assign any value, that will be assigned afterward. So 3 and variable 4, there is no value assigned to these two. So the logic is, if variable 1 is less than variable 2, then variable 3 will be assigned value 10, otherwise if the condition is false. So what we have to do here, move EAX comma variable 1, then we compare EAX and variable 2. So after comparison, what we have to do, so one thing here, what we are going to do is, we want to jump. So if it is less than, so here is, for example, if I say if it is less than or equal, for example, then if I want to write less than or equal to L1, I want to move towards the, or for example L1, and here less than or equal, then move to L1, otherwise move EAX, or not EAX but variable 1 or variable 3 is equal to variable 4 is equal to 5, and JMP is up to, for example, L2, and L2 is the next statement after this else, and so on. So here you can see L1, we want to write, for example, move variable 3 comma 10. So this is the same logic. If variable 1 is less than or equal to variable 2, so we have used the same logic. For example, move EX, for example, we compare here, first assign EX with variable 1, then we compare EX with variable 2, and so on. We jump to L1 if EAX is less than or equal to variable 2, so we will jump here. Where L1, so L1 means when the condition is true, variable 3 will be assigned to value 10, otherwise we will assign variable 3 and 4 with values 2 and 5 respectively, and then unconditional jump. So in this case, if condition is true, variable 3 will be assigned value 10, otherwise it will, variable 3 and 4 both will be assigned value 2 and 5. So just check this one. First we want to like build this one. So okay. The error is double word, so it should be not, I made one mistake here, it should be double word. So here is one mistake, so it's double word. I just build this one again, is successful. Run this again. So EX will be assigned the value in the variable 1, and the value inside the variable 1 is 4. Okay, 4 will be assigned to EX. Now compare with variable 2. Definitely they are not equal, so variable 1 is less than variable 1 is 4 and variable 2 is 5. So now we want to compare. After comparison, this jump will perform, jump less than or equal, and definitely if it is less than or equal, then it will jump to L1. So we will move to L1. You can see the cursor has come to L1, and variable 3 will be assigned value 10 and it will exit from the process. Otherwise, if I say variable 1 has the value 5, definitely the condition will be again true, because the condition is less than or equal here, or you can change the logic whatsoever you want to make it here. Now for example, the value is 6 here. To check either this condition fails, and then definitely the part in the else section here, the else section part will execute that. Variable 3 and 4 will be assigned value 2 and 5. So now we assign value 6 to variable 1, and variable 2 has the value 5. First we assign value of variable 1 to EX, that is 6. Now we compare with the 5. So after comparison, you can see jump LE will not be performed, and because the EAX is not less than the variable 2, or 6 is not less than or equal to 5, and so on. So variable 3 is assigned 2, variable 4 is assigned 5, and then there will be jump to L2. So this is the same logic which is implemented here. Now if I want to say I want to implement, so here we use the same logic, jump LE, jump to the L1. So the less than or equal is the same logic which we have used here. If I want to use the reverse logic, what will happen? So what I want to do here, jump greater than, for example, if I say jump greater than to L1, if it is greater than, it will jump here, and I will just move this code to at this point. So it will jump to, if EAX is greater than variable 2, or variable 1 is greater than variable 2, definitely this condition is not fulfilling here, so we have to perform this one. So we have used the reverse logic. Almost the code size is similar. We did not simplify this code at all. This is the almost similar, but we have used the reverse logic and so on. So if I just save this one, so if it is greater than, we have to move here to L1 and so on. Otherwise it will perform this condition which is in the if this condition is true, means it's less than or maybe equal. So we just build this solution is correct. So first EX will be assigned value variable 1, then compare with variable 2, jump greater than, so definitely is greater than, so we assign the variable 2 and 3 some values and then exit. Otherwise we will perform this one if the condition is true. So if the condition is true, for example, so we have to perform like 5 or 4 value here. We just build. Okay, so variable 1 is equal to 4, variable 2 is equal to, variable 1 equal to 4 and variable 2 is equal to 5. The same logic when this condition is true, so this jump will not perform. So this jump greater than will not perform. So we just build this one and we run this one. So EAX is 4. Now compare with the 5. So jump greater than, so EAX was 4 and variable 2 was 5, so it will not perform jump greater than. It will move 10 to the variable 3 and then jump to L2, so it will exit from the program. So this was all about this one, this whole statement when we have compound, when we use else statement. Now we are trying to move towards the compound statement. How we can move towards the compound statement, like if we have two compound expressions, for example we have two expressions and we have logic AND or OR logic which we use in them. I just copy this one, and what I want to do is to remove this. So this is the skeleton program. As you can see here, we have nothing in data and we can use any high-level language format for the compound statement, and there should be some logic like two expressions that we want to evaluate here, and it can be AND or OR operation. So for AND or maybe OR, we can use the, so these are the possible. In C++ or C we use $&% for AND and these two pipelines for the OR and so on. So these are the logical operators that we use, and we can use this expression here. So first expression, for example, if I want to use if BL is greater than, so if I want to use if AL is greater than BL and BL and CL, so BL is greater than CL, then something will happen here. Something must happen. For example, if I say EAX will be equal to, will be assigned value 22 in hexadecimal or whatsoever the logic you want to put here. Now it depends, either you want to use AND or OR here. For example, if I want to use AND or this sign, whatsoever the sign is, you want to use logical operator in C++. Okay, so 22 in hexadecimal and so on, or maybe simple 22 or whatsoever you want to. You can use variable 3 or so on if you want to write in pure. Okay, so what we want to do here, first move AL comma, we want to clear AX, EAX comma EAX, exclusive or EBX comma EBX and exclusive or ECX comma ECX. Okay, we have cleared all these three registers because we are using only 8-bit registers, so we want to check the values. If I say move AL comma 3 or 2, for example 3, move BL comma, for example this is 7, this is 6, move CL comma 5. Now these are the values which we have assigned, and now we want to implement the logic. So for example, this part should be above this one, So just check the logic, either how we are going to create the logic, or maybe we can shift this part also above this one. Okay, now we want to create the logic here. Now the logic is if BL is greater than 1, so what we say compare AL comma BL. If this condition is true, if AL is greater than BL, so what we will do, jump above to L1. If this condition is true, we will jump to L1. So for example, L1 is here. Otherwise, if this condition is false, so jump to next. So we don't need to in case if we use AND operation, if we use AND operation, we say that okay, first expression is true, it's okay. Otherwise, if first expression is false, we just jump to the quit from the quit 1 whatsoever. So quit 1 is here. So first we have to check the first expression. If first expression is true, then we have to go for the next expression. If the first expression is false, we can quit. There is no need to check for the next expression. Okay, now this is the first expression. I can write here in the first expression. Otherwise, if first expression is true, it will jump to L1. Okay, otherwise at the L1 what we are going to do is we want to check the next expression, CMP BL comma CL. Okay, so this is the second expression. So this is the second expression. Inside the second expression, what we are going to test, that if they are equal, we can say jump above to the L2. So L2 is the actual where this operation will perform, or the logic inside when two conditions are true. So L2, otherwise same jump to quit. If any of the condition is false or any of the expression is false, then it will jump to quit. Otherwise it will jump to L2. First condition is true, jump to L2 to check the next expression. If this next expression is true, then it will jump to L2, and here we can write, for example, move EAX comma the value which we have written here is 22, or variable 3. For example, if we define variable 3 double word, nothing, no values, variable 3 comma 22. Okay, so we just compile. First, this build the solution is correct and run this program. So clear all these values. AL is equal to 7, BL is equal to 6, CL is equal to 5. Compare AL comma BL. It has compared. If AL is greater than BL, it will jump to L1. So it will come here in the L1. Here it will perform BL and CL. Second condition has been compared. It will, if BL is greater than CL, so jump above will be performed, and jump above L2 has been performed, and we are now executing this statement, move variable 3 comma 22, and then it will continue the normal execution. So here you can see we have used this compound expression, and in this compound expression we have used AND operation, even though you can use OR operation here if you want to use. So in case of OR operation, what we have to do, if we use AND operation, or for example if there are multiple instructions here, you can use multiple instructions. It depends. For example, the next logic that we want to use in this one, the logic that we want to use, if we have EAX, for example, EBX is greater than, or for example, if I say less than or equal to, EBX is less than or equal to ECX, and EAX or ECX is greater than EDX. Okay, so ECX, EBX, and so this is the logic which I want to use here. For example, I just remove all this one. Okay, so we have values. ECX, for example, EBX, if EBX is less than or equal to ECX and ECX is greater than EDX, so we can perform this assignment. Variable 1 will be assigned 22 and variable 2 will be assigned 23 value. Now first of all, we have to assign some values to EAX, EBX and ECX, for example. So we want to exclusive R EDX also to remove the previous values. For example, EAX or EBX is equal to something like this one, and ECX is equal to 8 or maybe 7. Move the EDX with value, for example, 5. Okay, now these are the values. Now we have to implement this logic. For example, if EBX is less than or equal to ECX and ECX is greater than EDX, so this is the logic that we have to implement. For example, first of all we compare EBX with ECX. Now if I say if this condition fails, I will like jump above. So if this condition fails, we have to quit. So if I say jump above to quit 1, otherwise compare, we have to compare the next one, ECX comma EDX. Okay, so what will happen if jump below or equal, for example, if I say jump below or equal, quit 1. So in both of these cases, what we do, if this condition fails, the first condition, that if ECX is greater than EBX is greater than ECX, then we will quit. On the other hand, if this condition is true, and then we have to solve this, we have to find the value of this expression. If ECX is less than or below or equal to EDX, again we will quit. Otherwise, if ECX is greater than EDX, then we will perform the solution, like variable 1, move variable 1 with the value 22 and move variable 2 with the value 23, and so on. This is the most simple logic if you compare with the previous one. So this is the simplest logic. So variable 1 and variable 2. So we just build the solution. It's okay. So first we clear all these registers, then we assign EBX with 6, ECX with 7 and EDX with 5. Compare EBX and ECX. It has been compared. So definitely EBX has 6 and ECX has 7. So is EBX above? If EBX above ECX, no. it means the first condition here is true. Now compare ECX and EDX. If ECX is below or equal to EDX, no, because ECX is above, so ECX is 7 and EDX is 5. So we will assign these two variables, two values to these variables, and then we will quit. Now for example, if we assign 7 here to EDX, means this condition fails, but first condition is true, this condition fails. So what will happen? We will do one thing here. We just build this one and run. So here you can check first this comparison. So jump above, because EBX is less than or equal to ECX, so this condition is true, so jump above will not happen. However, this condition is false because ECX is equal to 7 and EDX both are equal to 7. So if I compare and it is not below, or if it will jump if it is below or equal. So here this condition is false, that ECX is not greater than EDX, so it will quit. It will not assign any values to these two variables. So this is one way you can implement. Similarly for the OR expression, you have seen that we have implemented OR expression. So I just save this one, and we can implement OR expression also. We just remove and we assign so this is new file. Here now the next that we want to implement high level logic is, for example, if EAX is greater than EBX, or ECX EBX is greater than EBX is greater than ECX, so this will happen. So now in this case of R, we have to test the condition. If the first condition is true, then we don't need to check for the second condition. We just continue with the expression, evaluation of the expression. However, on the other hand, and if we use AND, if first condition is false, there is no need to check, means whole condition is false. So here is the reverse logic, here is the opposite logic. Now how we can implement? So we assign values to EAX, EBX and ECX. So if I say move EAX comma 7, so we have to check the first condition. First condition is that if we compare EAX comma EBX, so we just check, jump above. If this condition is true, jump above to L1. So L1 is the expression where we assign values to. So here is the L1. Assign values to variable move variable 1 comma 22, move variable 2 comma 23, and so on. Now what we are going to do here is, so we don't need to go for the other condition. So if jump above, or if I say, okay, so if this condition is false, for example, then we have to check for the next condition, because maybe this condition is true. So what we do, we say EAX comma EBX comma ECX, we just compare them, and then if this condition is false, then we have to exit, we have to quit, because this condition has been false. That is the reason we came here. If this condition is false, for example, I will use the jump below or equal to quit 1. For example, if this condition will be true, for the second expression is true, then definitely this will be false because we are using reverse logic here. So definitely these two variables will be assigned some value. Now quit, we know that quit is here and it will exit from the program, for example. Now we will start with the execution. So EAX is 7, EBX is equal to 6, ECX is equal to 7, and so on. For example, we are going to compile this one. Build is okay, and here you can see. So we have EAX, they have been cleared. EAX is equal to 7, EBX is equal to 6, ECX is equal to 7, EDX is equal to 7, and compare EAX with EBX. So jump above to L1. If EAX is greater than EBX, it will move to L1. We don't need to check the next condition. So it will assign values and it will exit from the program. However, if this first condition is false, 6 is not greater than 6, and then here we assign 5, for example. We don't want to use this one, so we just remove. We just build this project, run. So first clear all the contents, assign values 6 and 5. Okay, first compare. Either EAX is compared with EBX, so we have to check either EAX is greater than EBX or not. So if it is above, then this jump will happen. If not, then we will compare the next condition, that either EBX register contents are greater than with the contents of the ECX. So we compare. So if this condition is false, for example, here is a 6, move EBX is equal to 6 and 5, EBX is equal to 6 and ECX is equal to 5. It means here we use the reverse logic, so we below or equal, then it will quit, otherwise it will move these two values to variable 1 and variable 2. It means this condition is true. This whole condition is true. EBX is greater than ECX, EBX is greater than ECX. It means these two variables will be assigned with these values and so on. Now this is all about the compound expressions and so on. Now what we are going to do, we are trying to have the while and the if and other, how we can use the while statement and so on, for example. Or I think we just use with the, I just stop this one. So this is the skeleton program. The name of this one assembly file is lecture 21 and 006.asm. So here we are trying to use the while expression. The while expression is like this one: while condition, for example, EAX is less than EBX. So if it is less than, so we have the loop, body of the loop. This body of the loop will execute. So in this body of the loop, whatsoever you want to write here. So this is the high level language format. So EX is less than EBX until and unless it will continue. So for example, if we want to implement without using the while directive, how we can use, we use top. For example, one level, we are starting our condition here. Before that, we will assign some values. For example, move EAX, comma 1, or maybe 0. Move EBX, comma 10. While we'll not use while directive here, so we use just compare EAX, comma EBX, and now this loop must continue until and unless this condition is true. Now if you want to exit from this loop, what we have to do, we have to have the opposite condition, or the condition when it fell. So jump, we say below or equal. If I say jump below or equal, jump above or equal, so it will jump to quit 1, for example, or quit 2. We will define quit 2 somewhere here. So quit 2 is here. Otherwise, decrement EX, increment EX, and we have unconditional jump to top. So EX will be incremented until and unless it reaches 1 less than the EBX. So what we are going to do here, we'll just build this project. So here you can see it's successful. Now what I want to do is I want to run. Exclusive OR, so EX will be assigned 0, EBX is assigned 10. So compare EX, EBX, jump if EAX is above or equal, quit, no, so we increment. So it will continue until unless. So this is while loop, it will continue until EAX is less than. So now EX is not less than, but so it will quit. So because it's now A, so if you want to use equal, less than or equal, for example here, then here it will be up to jump above. So this is the logic that you can use. For example, if you want to print this whole numbers, then how you can print, for example, if I want to use so here should be address. Successful. Now what does it will do? Here we can see, now this is the printing part. We want to print this message. If I want to display the contents of EAX. Okay, so we want to display the contents of EAX and this portion up to here. So before displaying the contents, we want to store the value of EAX, because when we perform std out or dw to a, double word, or to ASCII, it will change the values of EAX. So I want to save this one. I want to build the solution. It is okay. So I just run. I think now I have to move this one bit at the right side, or maybe I can bring this one on the top, or maybe here, so everything should be visible. So first clear the contents and then assign values. So jump, if we compare EX, so jump to quit, definitely this condition is now we have used less than or equal to condition, so it will print the values. For example, push EAX, invoke this one, std out, so 0 has been printed. We have popped the value, so you can see we want to increment, and then we want to jump again, so it will print 0, 1, 2, 3, 4, whatsoever the values up to 10 inside the up to 10 on the. So here one thing you want to notice here, if we want to perform dw data double word to ASCII, so it changes the contents. You can see EX has been changed. So the best way is the values of EX, ECX and EDX must be stored or pushed inside the stack before going to perform this std out and so on. So now it has pushed all these up to 10, now less than or equal, so now we have to jump to the top. So it was equal, but this is a lost value, it has been printed 10, so after 10 it will not print because it was less than or equal to condition. Or if you want to make it more robust or more clear cut, then out to byte is 13, 10, 0. So 13 is the 13 and 10, they are carriage return, and the line feed std out address out to, and here if you want to make it stop, so we can say invoke std in comma address. Okay, here we made the mistake, so this is case sensitive, be careful. Okay, so here we have missed how many bits we can input. So std out, out to, for example, is out 1 is 30, so we can use, for example, 30, and I want to build again. This is successful now, so now there is no need to run this one, so I can just directly, so you can see the output 0, 1, 2, 3 up to 10. I press enter, it will exit from the program and so on. So this is very simple. This is the same while loop, and you can write a procedure which just display the contents of EAX or any other register. so you can use that one here. Now this is while loop. Similarly, you can use the other loops. So this is where we print. I want to copy all this and then write the new program. Okay, so 6 is already available. Okay, here is this sorry. So the same program which we wrote previously, now what we want to do, we want to remove everything from here. Printing part should be there, and we want to remove this one. So now we want to use the directives, so there's no need to use this logic anymore. So now we want to use the directive. For example, we don't need this comparison. So this is to display the contents of EAX only. Now this is available here. Okay, so what we are going to do here, we want to use the if directive. For example, in Microsoft Assembly, we can use move EAX comma 10, move EBX comma 12, and if I want to use this if directive, if EAX is greater than EBX, then display, or I can say this variable 1, or maybe I can say ECX, move ECX comma EBX, for example EAX, otherwise. So else is move ECX comma EBX. So here we have and if. So can you see here we have used the if directive, else directive, and if directive. I just want to save this one, and I want to build the solution, and you can see what will be the output. I just execute. Okay, first one, move EX is equal to 10, so EX is equal to A, EX is equals EBX is equal to 12, or C. Now this if directive, if EAX is greater than EBX, so definitely EAX is 10, so it is not greater than EBX. So we have returned back to the next directive here after this is after this dot else. So it will, whatsoever the value is inside EAX, it will be printed. So this was the previous logic. So A has the value 10, so it will print, and it will wait for enter and exit from the program, and so on. So if, for example, if we want to write the logic to print the largest value, and EBX, for example, EBX is equal to 10, ECX is equal to 12. If EBX is greater than ECX, then EAX will be equal to EAX will be equal to EBX, otherwise EAX will be equal to ECX. So we want to have two values. For example, EBX and ECX, they have the values. what we want to do, we want to get the maximum value out of these both by using if statement, and then we want to print this value, for example. So here, if I want to run this program, build the solution, and I want to directly run this program, so it has printed value 12. It has printed value 12, if you can see here. Otherwise I can see the properties. If you cannot see, I can change the layout, so font, so if I want to use the fonts, the maximum size fonts, the full face fonts, okay, I want to change the size. So height is equal, for example, 80, and width is this one, so I think now it should be visible. If I say the properties, font, so this is okay. Colors, the display value should be this one, or maybe okay. So this is, I think, the perfect one. I believe this one is okay. So now we can run this one for, so we compare two variables by using if directive. If EBX is greater than ECX, so if EBX is greater than ECX, then whosoever has the greater value will be assigned to the EX. So if EBX is greater than ECX, then EX will be assigned with EBX. Otherwise, register AX or 32-bit register accumulator will be assigned with the ECX. So this is very simple logic which we have used, and this is to display the contents of EX register and so on. So if I change the value, for example, 44, build the solution, and if I run this one, so here you can see the output is 44 inside this one. So output is 44. It means it is going to check, find the maximum value inside this, inside the EBX and ECX. Okay, so if I just press enter, it will exit from the program. Now you can implement any logic by using if, else if, and else, and dot, and if. So these are the directives that you can use. Now one thing, we have used this directive, but the MASM or macro assembler generates the code, the same code which we generated previously, which we implemented. If you want to see that code, I want to show you right now. So here, whatsoever the program logic is, you use for this if EAX or EBX is greater than ECX. So if I want to see the disassembly, if you use go to disassembly, if, so first it will compare EBX and ECX, jump below or equal. If it is below or equal, it will jump to this at C001 or this address. So this address is this one. So move EAX comma ECX. Otherwise, this is the, if the condition is false, otherwise EAX will be moved with the EBX. So then this will jump to the next instruction. So the next instruction is C0CB101H, so 0CB1014H. So this is the logic you can see. It will compare, and it is also using the reverse logic. So here we use greater than, so it is using below or equal. So it depends what type of logic you want to use. So it is trying to minimize the size of the code. So assembler is efficient enough to minimize the size of the code to make the program more efficient, and so on. So this is the disassembly. You can see this disassembly, and I have shown you this disassembly. If I want to run again, I don't want to run like this one. I want to run the continuously. So here is the continuously. If you run, you will get the final value, and so on. Now this is about the if directive. Now for example, if I want to use the while directive, now dot, if I use while directive, and this is the same which will print the contents of EAX register. It will push the contents of EAX register without modifying them. So for example, if I say dot while, and this condition EAX is less than 10, here is the dot and while, but before this one, first I will say I would like to have move EAX comma 0. So while EAX is less than 10, I want to print all these values, or I want to print the whole value. So if I say increment EAX, okay, so now I want to build this one. Is successful. So it is printing all the values you can see here from 0 to 9, because we have used the logic less than. So this is the logic which you can see here. I don't want to see the registers right now. So if EAX, while EAX is less than 10, so if I use equal to, for example, I just press enter, I just build again, so it must print up to 10. So if I press F5, so here you can see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and so on. Similarly, after this while, if I want to use repeat all this until EAX is less than 10. So here what will happen, even if the EAX is, first of all I will just run this one, compile, and then I will let you know the difference. Well, so I just run, so it has printed out only 0 until EAX is less than 0. So it has run only once, so incremented this one. So I just put enter until EAX become greater than 0. So if I just build, I want to run, so here until EBX become greater than 10. So until this condition become true, it will repeat. Until this condition become true, it will repeat. If this condition is false, it will repeat itself when this condition becomes true. So it will quit from the program or quit from this logic. Here you can see we have incremented. Initially in EAX is equal to 0, it has repeated, and even though whatsoever the condition, for example, is first time, this will whole portion or the body of the loop will be executed. Now this repeat until will repeat until this condition reaches, this condition becomes true. If this condition is false, it will repeat. So if until EAX is greater than, for example, if I say greater than or equal to 10, and I want to run this one, first I build, then I run this one, so it will up to 9. So when this condition becomes true, it will not repeat itself. So this is the almost we did all. So similarly for repeat and while, if you see the disassembly, you will see the same code. So now we want to summarize the lecture. That in this lecture we have seen the implementation of bit test inside the assembly. So bit number start from the 0 and we can test any of the bit in either register or in variable whatsoever. And then we have conditional loop 0, loop equal, or loop not 0. So here is actually it is NZ and NE and so on. Then we have also tested the block if statements and also the compound expressions, how we can solve compound expressions. Then we have seen the while and repeat loops, and also we have seen the dot if, dot else, dot and if directives. Along with this one, we have used the while directive with NW, and we have used the repeat directive with until directive, where we have used the condition in while direction. So we have used all these conditional and the compound statements, and we have seen the expressions. Now this is end of this lecture, and inshallah hope to see you in the next lecture with a new topic in assembly language. Till next lecture, Allah Hafiz.